So the next change that I would like to attempt in this demonstration is that when the user is entering 3, 4, or any other value, perhaps what the user is expecting to see is how many times we actually play a single shot of the ball. So for instance, if I enter 1, maybe the program should only print ping. If I enter 2, maybe it should print ping pong. And if I enter 3, it should maybe print ping pong and ping again. In other words, I would like to individualize these words that the program is printing. So let's give it a try and try to make changes to achieve this type of behavior. There could be many different ways to do this, but having so far this ping function that prints both of these words, and remember, play count was here placed only for debugging purposes. So right now, the change that I'd like to make is, first of all, I just want to delete this play count from the output. I'm no longer going to do this, so I'm just going to completely do it like this. And also, I would like to create a copy of this function, basically copy its body, and paste it right here. And instead of printing ping pong, just print one word like this, and call another function pong, and print a different word. Okay, and here just use a space. So this way I am using two functions, ping and pong. So I'm just added a copy of it, and I'd like to stay on the focus of recursive function calls and observing calls and returns and passing parameters. So this is a perfect situation. So the only change that I need to make is that ping, instead of calling itself, now will be calling pong, right? So we say ping, we check the count. We call pong, we decrement the count. Inside the pong, we do the same thing. If we decided to print, we print the word, and then we call back into ping and say, okay, ping, take this new count and see if you want to deal with this, and whether it's something that you want to process or just want to return. So this looks pretty good, and we seem to be starting with ping the same way. We're going to always start with the ping in the current version, but then occasionally we'll be printing multiple words, and this time the count should control individual words. Also notice that I removed printing new line characters, so we just be printing the words on a single line when we go through these cout statements. So I just saved everything. This is the entire code of my program, and I'm going to say build, of course, because first I need to build the new version of the program. And I'm hitting this problem where the compiler tells me that pong function, this identifier pong, it doesn't even know that it's a function yet. But it complains that this identifier is not found. So of course there's a clue about it, that the pong function is defined beyond the point where it's being used, right? So it's defined later. We're trying to use this function to make a function call, but the compiler hasn't passed through the source file just yet and realizes that it still doesn't know what pong is. So the compiler refuses to build this program to process it, and complains that there's something wrong. Now notice, if we copy this this definition of this function, okay, just like this, and paste it at the top. So we say, okay, now let's define this function, but we'll be hitting the same problem with ping. So now the ping is undefined. Okay, so if I try building it again, now same thing with the ping. So the problem doesn't go away. And of course, it would be really a terrible programming language if you would have to rearrange the order of function definitions in your source file in order to somehow make it compile. So of course, this is not the way we're going to handle it, and it's really not solving anything. But what's possible to do is to copy the signature of the function, which includes the return type, the function name, the set of parameters, okay, and make a copy of it just like this, and take another function signature, copy and paste just like this, add semicolons like this at the end, and this now becomes a set of function declarations, or also known as function prototypes. Function prototypes or function declarations. So what does it do for us? Okay, so what it does, it allows the compiler to learn what, first of all, it knows that pong is a function because it has the opening parentheses. And if we have a declaration like this, the opening parentheses inside the declaration may only declare a function. And likewise, we can declare function ping. How these declarations are useful? Apparently, because now compiler knows for sure that this is a function and this is a function, it also knows the set of parameters. So remember, to call a function, compiler really only need to know what are function parameters, because all function calls look alike when the program is compiled. So therefore, if we simply tell the compiler beforehand that these are two functions and they're expecting these types of parameters, it will be able to generate the code needed to make function calls without complete definition of the functions. So then, when we proceed down here, so something that looks like a function because it has parentheses and has the opening brace and the closing brace, the compiler knows that this is a complete definition of the function. So these are function definitions. Okay, and so the function definitions provide information, complete definition of the function, about what kind of steps, what task this function is trying to solve in terms of a set of statements that are present in this function. So now, if we try building this, okay, and so I will try to my best to fit this program in our view. Close this, and so let's again run this without debugging, just to see quickly how everything works. So I'll say just debug, start without debugging. Control F5 is the shortcut for this option. All right, so here we have our friendly view, and I'll say, okay, let's play 5 times. You see what happens? So now we play ping pong, ping pong, ping. So this is exactly 5 words that are being printed, right? So this may not be exactly ideal or perfect solution, but it's actually very effective in our situation because we deal with these recursive calls. And it's okay to have functions that look very, very much alike, but they accomplish the desired implementation of the logic that we're trying to achieve quite nicely. So we're printing everything as expected. And of course, if I press 0 to exit this program, and of course, if we try to run this program in debug mode, I'm not going to do this right now, but the same thing will be happening according to the play count. So this time, basically, the play count calls into ping first time, right? So it makes initial call right here. If the count is non-zero, of course, it will call pong like this. Okay, and if the count being decremented is still not 0, so we have some values to consume here, then pong will actually call ping, so it will call here, right? And the ping will continue to call as long as the count is non-zero, and this will continue, and eventually they all will return okay, depending on what is the initial count entered by the user right here. So it's very possible that if we enter a big number right here, our stack frame can look like this. You know, it could be a lot of stack frames that will be placed on the inside the stack memory segment before all of these functions eventually return. In this situation, when one function calls another function which has the potential to call back into the same function, we call it indirect recursion. In our prior version of the code, ping was calling itself, which is a direct recursion, or just recursive design to call functions. Here, because one function calls another and that other function calls back into the original one, this is called an indirect recursion, which is by nature is pretty much the same. We still have to have all of the conditions checked in order to be able to properly return from the chain of function calls, because if we do not provide proper condition checking upon entering the function or elsewhere, we will be in trouble, because eventually if we just keep calling and calling and calling, apparently this will be a logical bug in our program, but also it will eventually lead to exhaustion of the stack frame memory. In fact, let's observe how it looks like if we temporarily just comment out, pretend that we forgot to place our if statements inside our functions. So now there is no stopping condition. We just keep calling and calling and calling, right? So all of the functions will be doing just print something and then keep calling themselves. And we will now build it again like this, and let's run this program right now, and I will run it in debug mode. I will just delete this breakpoint because I really don't need it, but I will press F5, or you can click debug, start debugging, and debugger should be able to detect exhaustion of the stack memory because of these runaway train of the function calls. So let's start debugging. So it's asking us how many times to play. It doesn't really matter. I'll just say 1, okay? But look, the exception that happened in the end of this is something that says stack overflow, and this is a special type of exception number, and we've got some really long way of, really long list of function calls on the stack before the stack exhausted, and there was no more space on the stack to accommodate frames of function calls that contain all of the local variables. And of course, this is a logic bug, but it also leads to a physical exception, like basically the program has crashed. Essentially, when the stack overflows, the CPU, our chip, our processing unit, notifies the operating system about the program behavior like this and says this is unacceptable, and the operating system pretty much removes the program from the memory, and the program crashes. There will be a message to the user that there was some kind of problem like stack overflow. I don't know what is how descriptive that name is going to be, or description overall, but in debug mode, the result is quite obvious. There was something that ended up with a stack overflow